So, to start this session, I wanted to start by trying to answer two of the questions that we had this morning. And I've forgotten what they were now, but that will come to me now. So, yes, one of the questions was, you remember this map which shows the parallax differences between two solutions using two subsets of the data, the early and late part of the field of view. And one question was, how can, for example, chromaticity in the instrument cause systematic differences between these solutions that are different in different parts of the sky? And it's an interesting question, and I'm not studied it deeply, but I think it can be understood from the way the parallax determination is done. Parallax is determined by a least square solution of the different scans across a given star. And that means that basically the displacement in the field of view is a certain linear combination of that gives the parallax for that star. And these different linear combinations are different in different parts of the sky, depending on the scanning law and the time distribution of the scans and their directions. So if you go to just 30 degrees away from the point, you have a different set of scans at different times. And the linear combination of the observations that make up the parallax is something completely different. And that means that even if you have, for example, for blue stars, a systematic displacement always in the same direction in the field of view, when you do these different combinations, linear combinations, it will give a different parallax bias. And this will also be different for stars of different colors, of course. And one way of testing that is actually to look at what happens at opposite sides of the sky. I mean at a separation of 180 degrees, because the parallax factor is just of the reversed sign at that point. So that means that a given displacement in the field of view will generate a parallax error with the opposite sign in the antipode, so to speak. And I think to some extent you can perhaps see something like that in a plot like this. But I spent 6 hours this night while I was sleeping computing the two-point correlation function of these parallax differences, and I didn't have a very efficient algorithm. It was done very simply in MATLAB with a double loop, so it took quite some time. But the result is very interesting. I have not done this experiment before, so this is something that you are going to see for the first time now, what this looks like. So what I've computed is the covariance between the parallax difference at two different points in the sky as a function of the angle between the 2 points. And it looks like this. So you can see that if the angle is small, if the 2 points on the sky are close, you have a positive covariance between them. For small angles, it goes up to about 0.006 to 0.008 milliarcsecond square. And that corresponds to an RMS contribution of the order of 0.1 milliarcsecond. So that is a typical RMS contribution all over the sky from this kind of systematic that was displayed in the map. And then you see that this covariance goes down to 0 and even slightly negative values at an angular distance of about 40 degrees. And then it is almost symmetrically mirrored in the other direction, so that you have a negative covariance in the opposite And that agrees with my hypothesis that the same systematic displacement in the field of view creates parallax biases of opposite signs at 180-degree distance. Yes?
So one obvious from the first four fields and the next four is that the latter are more distant from the skyline. So could it, if there is any drift in the if there is a drift in the position, and that's not completely taken into account, could that produce an asymmetry? Because then, of course, the satellite always spins the same direction. There is a fixed relationship between the spin axis and the sun. So I could imagine that propagating into some kind of systematics like that, but I don't know if it's possible.
No, I don't think that. I mean, there could be some such effect, but I don't think it is important. A much more important effect is that the optical center of the telescope is in the later part of the field of view, because it is more or less the center of all the CCDs. And the chromaticity is, in fact, much stronger in the first part than in the second part. So, any more questions about this? Do you think that this is a reasonable explanation of why this map looks like this? Alex?
I just have a remark. I think we have done runs with color, validation run with color term in the calibration, and if I remember well, we see similar pattern. Not exactly the same, but something similar.
Yes, that's correct, yes. But I have not tried to compute the covariance function for that. Okay, so one other question that was, I should say that I will take up these two questions, and then after that, let's have a question and answer session. One other question that came up is, how is it possible that on one hand, we are told that the systematic errors of 0.3 milliarcsecond should be added quadratically to the formal errors, but on the other hand, we see in at least some cases, like the Cepheids and our there are evidence that the formal errors in DR1 are actually overestimated by some 20% or so, because you get a smaller spread than you expect there should be. And that is a bit of a puzzle, but to discuss that, I would like to take this opportunity to explain a little bit more carefully how this calibration, as I called it, was made of the formal errors by the comparison to the Hipparcos catalog. So I have a few slides about that too. So the starting point is this diagram, which I showed this morning, where this part here gives indication that the Gaia parallaxes are more accurate than the Hipparcos parallaxes for this selection, which is, I've checked this, it's 86,000 stars in common between the two catalogs, where the formal errors in the Hipparcos catalog is less than 1.5 milliarcsecond. Another way of plotting this exactly the same diagram is this, which Xavier also showed. So this is the Hipparcos parallax, and here is the difference between the two parallaxes. And if you, I mean, So these two quantities are correlated because the Hipparcos parallax appears on both the horizontal and vertical axis, and in fact this line here corresponds to 0 Tigas parallax. Now if we arbitrarily select parallaxes less than 4 here and just compute correlation coefficient of the points to the left of that. We find the correlation coefficients of minus 0.5, which corresponds to that we have this Q distribution there. Now, let me generalize this diagram a little bit by plotting not the Hipparcos parallax here, but the weighted mean of the T-gas and Hipparcos parallax, where the weight factor for Hipparcos is called X, and for T-gas 1 minus X. So X can vary between 0 and 1. And in this case, it is 1, which means that we have the Hipparcos parallax on the horizontal axis, and we always have the difference in parallax on the vertical axis. So in this case, to the left of 4 milliarcsecond, we have a correlation coefficient of minus 0.5. Now, I will show what happens when I successively decrease this value of X to smaller and smaller values. You can see that the correlation decreases, and at a certain point about here, there is no correlation virtually between the weighted mean parallax, and the parallax difference. And that corresponds to X equal 0.1. And if I decrease it further, you can see that there starts to be a positive correlation. So in this case, I have T-gas parallax on the horizontal axis is X equal to 0. So how can we understand this? Well, it's actually very easy to show that if we assume that the errors in the T-gas and the Hipparcos parallaxes are mutually uncorrelated, which is reasonable because they are from two completely independent missions, and we have not used the Hipparcos parallaxes in T-gas, only the Hipparcos positions. We also have to assume that the errors are uncorrelated with the true parallax, so, which is also a reasonable approximation. Then, obviously, the variance of the difference in parallax between the two is the sum of the two variances. But you can also easily show that the covariance between the difference and the mean value is 0, that if the covariance is 0, then the ratio of the variances is x to 1 over x. So if we determine that we get 0 correlation when x is 0.1, it means that the Hipparcos variance is 9 times larger than the T-gas variance on average. And that means that the sigmas in Hipparcos are 3 times larger. So here we have a way to determine both the sum of the variances and the ratio. And it means that we can determine the variance of both samples.
Don't you store everything in one basket?
No, I don't. What I do then is to divide up the sample in cells depending on the formal error, both in T-gas and Hipparcos. I have a number of different cells here. And for each of the cells, I determine separately the formal parallax variance of the T-gas parallaxes and the estimated variance based on this formula. And what I get then are these blue points here. And the red curve is the fitted relation, where I add quadratically 0.2 milliarcsecond to all the formal errors and multiply them by 1.4. And that gives the calibrated uncertainty of the T-gas parallaxes as given in DR1. And if you don't like this manipulation, this is a formula that can easily be reverted, so you can calculate back the original formal parallax sigmas in T-gas by inverting this formula. So that was how it was done. Now, as Flor said, this was done by considering all the parallaxes, all the Hipparcos subset together, and mixing all the stars. But we know that things depend on many other things, like the colors, for example. I don't have this plot here, but may remember the plot I had of the excess noise as a function of color, where you could see that it had this U shape. It increases with extreme colors.
No, presentations.
Well, no, I don't need to show it, really. One possible explanation for this overestimation of the errors in TGAS could be that this calibration was done for all sorts of colors. But if you then look at objects with more or less average color, not extremely blue, not extremely red, then it could be that this actually overestimates slightly the errors in TGAS. And I think both Lyra and Cepheids are in the middle color range. They don't have extreme colors. And maybe that could be an explanation.
I mean, at least for the Cepheids. Yeah, they're fairly middling colors too.
Yes.
G-stars.
Yes. So that's just a hypothesis. Perhaps it could be tested a little bit more, but that's a possible explanation. So I think the errors given in the catalog are based on discussions like this, which use the whole sample and may not be applicable to a subsample of, for example, a specific color or something like that.
But what I hear from Michael Feast is that our Lyra situation is not a slight difference, it is a huge difference compared to what's being expected. I mean, he finds, he looked at the RLI rays that were also given a distance by the Bada-Wesseling method, about 19 of those. They have parallax between 0.5 and 2 milliarc seconds. There's a standard deviation on those parallaxes. Well, first of all, the difference between the parallaxes that were determined in the Bada-Wesseling and what's found in TGAS is remarkably small. It's less than a hundredth of a milliarc second, systematically. The standard deviation is around 0.13 milliarc second, which is not just a little bit different from the 0.3. It's a huge amount different.
Mm-hmm.
How can you get such good agreement with theoretical parallaxes, where you expect cosmic noise, where you expect almost anything to come in? Very good agreement in the mean value, far too good agreement in the dispersion. Where does that come from?
Yeah, I don't know.
Suspicious.
I don't know. No, I don't have any suspicions. I don't know. Maybe somebody has a good idea about that. Yes. Stefano.
I cannot answer that particular question. The situation with the Cepheids is not quite so extreme. We just find about a factor of 0.8 in the error. So would be about half your inflation factor would match pretty well. One question I had though is, after you apply this formula, and let's say that's the right formula, let's say these are the correct errors without covariances, etc., just the correct TGAS errors. If you then go back and do the same analysis done before, does that now come up with the correct with the correct no covariance?
Yes.
Okay, because that doesn't automatically follow. Follow here. So you've done that, and it
Yes.
actually.
So, okay, now this, I don't have a resolution for this problem, why it is so small. But
Some Cepheids may have extreme colors because they may be reddened. That's not quite the case for our Lyra, but some Cepheids have high reddening.
Yes,
So one
okay.
may want to look at those and exclude those in the comparison.
Mm-hmm. Yeah, okay. But now I would like to come back to this question about what to do with the 0.3 milliarc second systematic error. If we accept that the Hipparcos catalog does not have any systematic errors of that kind, at least, then the global comparison with Hipparcos done here should, in principle, include everything, not only the random errors, but also the systematic errors. And this 0.3 milliarc second should already be included in these corrected values, as far as I understand. And I think it is. It's just that it is not 0.3 milliarc second RMS, because these 0.3 milliarc second don't apply to more than a fraction of the sky, really. Most of the sky, it's more like 0.1 milliarc second or so. So what is quadratically included in the errors, uncertainties in the catalog is not 0.3 milliarc second, but something more like 0.1 milliarc second, maybe. And that means that I think it would be wrong to add an additional 0.3 milliarc second RMS to them. And that would make the situation with the Cepheids even much worse, of course, as you pointed out. Right, any more thoughts about these things?
Well, I often get the question what to do. So this, I think I agree that just adding them in quadrature, the systematic errors, is not a good approach, especially, of course, if you look at small areas. But then people always ask, what should I do with the systematic errors? The only answer I usually have is perform your analysis with the random errors that we quote in the catalog, and just keep in mind that any results you find might be affected by systematics. But I don't have any better advice than that at the moment. I don't know what your thoughts are on this.
Yes, I think that is the only advice that can be given, maybe.
So I've said it, I think, before. When I look at the star clusters, I've got 19 clusters. Sorry, when I look at the star clusters, the comparison between the parallaxes for the 2009 Hipparcos determination and the new TICAS determination, you need something like a 0.25 milliarc second extra noise to explain the differences. Where the 0.25 exactly comes from, I don't know. Whether it's the pure TICAS or partly TICAS, partly Hipparcos origin, it's unclear. But it indicates a rather smaller than a larger error that is to be added.
Okay.
Individual per cluster, the parallaxes have accuracies of the order of a few hundreds of milliarc second. Yeah.
I should mention that when doing this analysis of the differences between Hipparcos and TICAS parallaxes, I get, of course, also estimates of the errors in the Hipparcos parallaxes. And they are systematically about 7% larger than in the Hipparcos catalog. So maybe these 7% on top of something between 0.5 and 1 milliarc second would be sufficient to explain this discrepancy that you find.
I don't think I would have been able to.
Lennart?
Yeah.
Sorry, now you got me a bit confused with the last statement. In the paper from Anthony and my slides, we recommend to add a random term and systematic. Systematic is 0.3. But now you say this 0.3 should not be added?
Well, what I'm saying is that we don't know what the systematics are, but if we think that they are something similar to this map, or other similar maps that we have produced, including and not including color correction in the calibration and so on, they always, or most of the time, they have similar character. It's large-scale features of the order of tens of degrees, and the total amplitude of it is of the order of 0.3 milliarc second. If we think that that is representative for the actual parallax errors, then that means that the RMS bias is not 0.3 milliarc second, but much smaller, maybe 0.1 even. So if what I'm saying is that in principle, this is already included in the published errors. And therefore, I think it would be wrong to add it on top of it. even this 0.1 milliarcsecond. But it would be even more wrong to add 0.3 milliarcsecond on top of it.
Yeah, I think also, I'm going to get away from the intention, at least in my mind, with this sentence about, quote, random plus systematic component was to make sure you keep in mind that there is this systematic component, but the intention was not to add them in quadrature. But that might definitely be the way people interpret this.
It depends, of course, what you are using the data for. If you are doing a statistical analysis where you are concerned about that you not only get realistic errors, but that you don't overestimate them, then you should definitely not add it. But if you just want to have a kind of safety margin on an individual object, maybe that is a good way of doing it. So there are several people who wanted to...
Maybe then I need to clarify the slide I presented this morning, where I made the comment for individual stars, adding the 0.3 as a safety margin is okay?
For an individual star, I would say that is maybe a reasonable thing to do.
And for averaging parallaxes?
Well, yeah, it's the same argument. When you average parallaxes, you don't decrease the systematic errors. So what that means is that we don't really know what the error is of an average parallax, because it depends on the detailed correlations and so on. We can possibly put an upper limit, which is if we assume that the systematic errors goes in the end to the average, or a lower limit if we assume that it goes to the individual stars. But where we are in between, that is very difficult to say. I would not like to give a recipe for how to compute the uncertainty of a mean parallax in general. Yeah. That would require a much deeper analysis than just applying some rule of thumb formula.
I agree, Lennart, that it's a complicated discussion, and we see that not even the experts are really giving the same answers on that. But the danger of that is, of course, that everyone does its own recipe, because there is no advice on that. And I mean, the question is whether one should at least give some result of that discussion to the documentation added, a little bit more careful discussion that is available for all users. I mean, that will go down with DR2, very hopefully that the systematics will not play the role. But as long as DR1 is used for scientific usage, I think some general statements on how to do that is very, very much needed.
I don't think you can make general statements. That's the problem. It really depends on what kind of analysis you're doing.
Yeah.
And you just have to, in the back of your mind, that there are systematics. So if you find a surprising result, it could be related.
I mean, for our white dwarf paper, we added the 0.3 mass, which is maybe fine, because in that case, the chromaticity effect may be even underestimated for the few stars that we have. But I mean, it will create some confusion, definitely.
Okay, there was a question in the back.
Oh,
Have you resolved it in the meantime?
I just wanted to mention that there's 2 papers on the archive with 2 different sets of parallaxes for independently measured parallaxes. One is using eclipsing binaries, and they find a offset of about 0.25 milliarcseconds, in the sense that the Gaia parallaxes are 0.25 milliarcseconds smaller than the distance that you get from well-measured eclipsing binaries. And it looks like there's also another paper on the archive using a different set of data with nearby solar neighborhood stars, and they also find an offset of 0.25 milliarcseconds. I was just wondering if you could comment about that.
Well, concerning the eclipsing binaries paper, I think if you look at the diagram they publish of the parallax difference versus the size of the parallax from the eclipsing binaries, you will see that for the small parallaxes there is no offset at all. The large offset of minus 0.25 milliarcsecond is only for the stars with parallax larger than 1 or 2 milliarcseconds. And I think that offset is better explained by a scale error in the eclipsing binary distance scale, which could be caused, for example, of wrong effective temperatures or something like that. And I think they discuss that possibility but dismiss it for various reasons. But I think to explain it as an offset in the T-gas parallax is not the first explanation I would look for, because the small parallaxes agree perfectly with, for the distant eclipsing binaries, it agrees perfectly with T-gas.
So what about the other paper that's on archive that involves 612 stars with parallaxes for stars nearby, and they find that offset also?
I'm not so familiar with that paper, and I've forgotten what these distances were based on.
There are parallaxes measured for solar neighborhood stars with other telescopes.
But
I saw it on AstroPH only today. I think it's a very recent paper.
Okay, I have not seen that. So
I will show tomorrow for the concerning the validation, all the different comparisons that we did using spectrophotometric parallaxes, R-arrays, cepheids, and so on. So we have done a lot of tests, and I will show tomorrow the value, but nowhere we get a 0 point that large. And indeed, I think that the explanation of Lennart is correct. When you do the comparison between your own data and other data, you should remain always humble. That is adding a 0 point in the other data and a 0 point in your data, and solve for these two parameters. And then in that case, I would like to see what was the 0 point for the absolute magnitudes in the case of the eclipsing binaries. Now to come back to the question of the 0.3, it was a conservative value found using the sample of QSOs. 0.15 was found, and I think 0.3 was conservative to cope with very large errors that we could have, very large systematic errors we could have.
Yeah, I had I guess a question about the process of deriving the inflation of the errors by requiring the covariance between Hipparcos and Gaia to be small. So the issue with the Cepheids, it seems they have generally very small parallaxes. Almost all of them are, something like 0.5 milliarcsecond. It seems like Hipparcos would be weighted towards larger parallaxes. So I guess I'm wondering about a scale dependence of the error inflation, if it's essentially being trained at large parallax and the discrepancies we're seeing are at small parallax.
I'm not sure I understand completely. I mean, the 0 point error in Gaia or Hipparcos may depend on many things like magnitude, color, and so on, and position on the sky, but I don't think it could depend on the size of the parallax itself.
Okay.
So there is no reason to expect that the 0 point would be different for distant stars or nearby stars, unless they differ in some other respect as well.
That they're in different distance regimes. It may not make any difference.
I don't think that should make any difference, no. Not unless they also differ systematically in color or magnitude or something like that.
Your graph that you showed of the equation you need to make the covariance go away, right, is a function of parallax error, and so I thought different parts of that, the data, you might fit with a different relation, and the function you actually have might not be the true function, so that it would be a systematic error in fitting that function.
Yes, I'm sure there is that kind of error. And of course, the more distant stars are on the average fainter, and therefore they have larger formal errors already from the photon statistics, and therefore this correction factor is different and maybe not so correct for them, or better for them, or I don't know. So there are many kinds of dependencies like that to take into account. Yeah.
I just wanted to mention that regarding the 0-point error, as far as a small sample of Cepheids, it's completely consistent with zero error, like 6 microarc seconds plus or minus 50, I remember the number, and Adam is going to present that tomorrow. So there's no attempt to discriminate between north and south or versus color or anything like that, because only 200 Cepheids. But essentially, we do not see any 0-point error.
Yeah. There are not by now a number of studies that seem to converge more or less on that kind of result, or perhaps something between 0 and minus 0.1, depending on what objects you have and part of the sky and so on. So there is probably some sort of global 0-point error, but it is probably less than 0.1 milliarc second, I would say.
I just want to stress that if you de-inflate the errors, you will get formal errors that are too small, because these formal errors are only for each sources, and do not include modeling errors in the attitude or in the calibration. So just a point.
Well, to some extent, they include the modeling errors via this excess noise. That's something that I forgot to mention this morning, that we estimate this excess noise, which is added to the photon noise uncertainties of the observations in order to get the unit weight variance correct. But then that is also used in calculating the formal errors of the astrometric parameters. So in case there are modeling errors in the attitude and the instrument, they do come into the error budget also for the astrometric parameters, but not enough, which could be a sign of that we still have not sufficient redundancy of observations or whatever to cope with it completely.
And that noise is added per source?
Yes.
Maybe this has been asked earlier, but I'm a quasar guy, so I'm curious. If you pulled out the set of quasars that you know and looked at parallax and see if you get something consistent with 0?
Yeah, actually, Xavier showed exactly that diagram earlier this morning, and it is, I've forgotten, the median is minus 0.05 or something like that milliarc seconds, with a dispersion of the order of 1 milliarc second.
Are you showing it again tomorrow, Frederic? Yeah.
How was it?
View and then. Yeah.
This one?
No, I meant the distribution, yeah. That one, yes. So this is the distribution of the quasar parallaxes, about 100,000 quasar parallaxes. So this is very close to 0. But one should be aware that the quasar solution is very different from the TIGA solution. It uses a completely different prior. So it's not clear how representative this is for TIGAs. And of course, quasars are crazy objects in other respects, also colors and structure and so on.
This is from the auxiliary solution?
Yes.
Sorry, the auxiliary solution? It's a few thousand quasars, isn't it?
No, it's actually about 100,000 quasars. Okay. But we only published the 2,000 in ICRF.
Were you going to say something else? No, I want to come back to the question I asked you this morning, since it's discussion period, about the fact that your residuals are not normal but you're still using a chi-square, which I'm saying, I was saying something more appropriate in the sense that you could construct an empirical distribution function and use that to construct your likelihood function and minimize that.
Yes.
So
I agree that that is in principle possible and would be more optimal. But I think it is practically much more difficult to do. And I don't think we will do it even for the final release. And of course, I hope that as the modeling of the instrument and the sources gets better and better, the residuals will become almost Gaussian, so that it's appropriate to use a chi-square with rejection of outliers will always be necessary, of course.
It is a very large optimization problem we are doing, so that's one of the reasons not to look for more appropriate
So
methods.
we have about half a billion unknowns when we do the full-scale solution.
Something different. Did anyone compare yet the parallaxes of the original Hipparcos solution versus the 2007 version of Hipparcos with respect to Gaia? Gaia being the truth, more or less. Is there any difference?
Well, I think we know that there is no systematic difference between the two Hipparcos catalogs. But I don't think anybody has actually done that comparison directly with TGAS. Now, all three catalogs are in GACS, so it's easy to do it. So I invite everybody to
nice
try
top-hat
that.
exercise, Norbert. You can ask, there's...
I had a discussion earlier with Xavi about, well, what I'm interested in is the astrometric measurements leading to potentially in the future detections of exoplanets. Of course, we can't do that now with the, which is, but so what I was hoping to understand from this workshop, and I think I have pretty much the answers by now from these sessions, is that the uncertainties in the astrometric positions at the moment don't allow us to identify any sources that could be potential candidates for being a binary or something like that to a ratio of about 10:1 mass ratio. So for a solar star, it doesn't put us in the planet regime, but rather than a very low. So that's just a summary of some discussions we've had before.
I think that's a correct conclusion. Yeah.
Yeah. So I guess the only follow-up question I would still have, and I guess that's easy to work out, is how much will this improve in the second data release? So I think towards the end of your talk, you mentioned some of the numbers that you expected for the precision.
Yes. Now, in order to do that kind of analysis, are you thinking of finding candidate stars from the excess noise, for example? Yeah, but yeah, I don't know. Maybe it's doable, but you would probably end up with a sample of many millions of candidates. So that's probably not very useful.
No, I have my candidates.
Okay, right. Yes. I would expect that also data release 2 is not terribly sensitive for mass ratios larger than 10.
Another question. So you talked about the excess noise that you use, and then you said, and then there's some other down weighting, and I was wondering if you could be more explicit about that.
Yes. So, okay, now I have this morning's presentation here, so I can take advantage of that. So once we have adjusted the sigmas of the observations with the excess noise, we still have some observations, of course, where the residual is many times larger than this combined sigma. And they are down-weighted with a formula which is, I mean, weight is basically 1 out to 3 sigmas roughly, and then it goes exponentially down for larger sigma. So at the sigma at the residual of 10 or 20 sigmas, the weight is essentially 0.
I guess I don't quite understand. If you've used the right value of excess noise, doesn't that limit the residual to be of order the combined formal and excess noise?
Well, it depends on, I mean, a star typically has, in the end, some 800 observations. Now, if 1% of them sticks out by 10 sigma, they are very easily identified, and you can see that the rest only needs an additional excess noise of 0.1 milliarcsecond.
I see.
That is the normal situation, but then there are some stars where virtually all the observations.
So there's sort of two flavors of excess noise then, the sort of at the internal and then in the whole solution?
No, they are all in the solution for the star itself.
Okay.
But it's more a question, does it apply to
all
or most of the observations of the source,
Okay.
or just to a few isolated observations?
Okay. Is this done by hand, or is this a sort of code?
No, there is an iterative code doing that. It's a fairly simple procedure.
And what is the sort of dynamic range of the excess noise that you see? What does it range from?
It ranges from, well, in this first DR1, it ranges from, as you can see here, from, well, ideally it should be 0 for many sources, and I think for the secondary sources it is 0 for many sources. In TGAS it's only 0 for 3 sources, I think. So the smallest value is typically then 0.1 milliarcsecond, and the more typical value is 0.5, and then for some sources it's 5 or more milliarcseconds.
Can I show a figure on yeah? It's a figure I wanted to show you this morning.
Yeah, okay. Yes. Oops.
So, as we're anyway talking about excess noise, this is the excess noise as a function of position on the sky for those stars that have Hipparcos first epoch data. And that's what made me worried, because the highest these are average excess noise levels over areas of about 2 square degrees. Yeah? And the highest excess noise you find always there where you get most observations. Yeah, so these areas there around, it's the ecliptic pole scanning mode, that's where you've got most observations, and then there are other areas too. And this you only see for those data which have Hipparcos first epoch positions. And that made me wonder, what's the reason behind this part? Yeah, because if there's excess noise coming up with increasing number of Gaia observations, it means that there is a friction between the Hipparcos first epoch position and the Gaia data. Yeah, and I don't know what other consequences that friction may have. Because the prop motion that you get is determined, the parallax that you determine for those stars is largely determined by the prop motion you set based on the Hipparcos first epoch combined with the Gaia data. So if there's friction in that sense, then you may expect also some systematics on the parallaxes this way. And I seem to recognize some of these areas also in other diagrams.
Yeah, I don't have an explanation for this. I mean, we have seen in many situations that the ecliptic pole scanning, which you see clearly outlined here, that's this part that goes up there and then out on the other side. That's ecliptic pole scanning. That is very problematic, and that has larger excess noise generally, and don't know exactly why.
Also here and it's also there.
Yes, that's at the plus minus 45 degree ecliptic coordinate, yes, ecliptic latitude. I don't know. There could be several reasons for that. One reason could be that the propagation measured by Gaia is simply not quite consistent with the mean propagation over the 25 years. Maybe because it's a binary or something. And that would show up with more and more clearly the more observations you have. But the fact that it is so clearly along the ecliptic pole scanning, that suggests to me that it is more a kind of systematic errors in the Gaia data, probably related to the chromaticity again. I mean, in the other diagram I showed with the difference between the early and late, we also could see this ecliptic pole scanning quite clearly outlined there.
It's the number of observations.
Yes, yes.
But it's like this where the scans are going forward along scans. It's in the acoustics mostly.
It's, I don't know if it is relevant for this, because these are the places where the when you are at these plus minus 45 degrees and you get many observations there because of the scanning law, then the parallax factor along scan is 0. And the parallax factor along scanning, the ecliptic pole scanning, is also not 0, but small. So maybe it is connected to that somehow. I don't see exactly how, but I suspect that, again, it is related to the instrument calibration. I think we simply have to wait for DR2 to get the resolution for many of these questions.
The HIP parameter, Hipparcos solutions are used as a prior while calculating the TGAS solutions. I think that makes a lot of sense. At the same time, the Hipparcos parameters are themselves calculated from many individual observations each from the Hipparcos satellite. And so I wondered if you had thought about, or whether it makes sense to pull those individual observations and do one master regression over all of them, rather than kind of doing a two-stage regression.
Yeah, we have thought about that, but we don't think it's worth the effort. It's too complicated, and even to, I mean, the modeling is so different in Hipparcos and TGAS of everything, attitude, instrument, and so on, that it would be a huge complication. I think the important information is preserved in the astrometric parameters, the covariance matrix from Hipparcos, and that is all that we are using.
Even more, in the next release, you don't plan to use at all Hipparcos of Tycho. So.
Yeah.
I've got a more specific question about what to look forward to in the DR2. Two questions. One's pretty simple. I noticed you have in database a field for the epoch. Are you expecting in the DR2 that the epoch will not be constant?
Sorry, I didn't hear that quite.
In the DR2, are you going to have a constant epoch catalog in the database, or are you going to have a different value in the database field?
No, I think it will be a constant epoch for all the sources, also in DR2, I think.
Okay. The second question is, a lot of what you've projected so far is about how good the proper motions in parallaxes are going to be, but I'm actually more concerned about the positions, the scatter, the noise on the positions. Let me just pick a magnitude range that I care about, which is sort of like 18th to 19th magnitudes, kind of towards the faint end of the catalog, but not in the weeds. So right now I'm seeing something of the order of 10 milliarc seconds for the scatter and the positions. What can I expect that to drop to for DR2?
Just from the top of my head, I would guess around 1 milliarc second.
Okay.
Factor 10?
Yes.
How's that with only twice the observation?
Well, remember for these faint sources, we don't have, we are using this galactic prior, which means that the errors given include a contribution from the unknown proper motion and parallax. So if we actually make a 5-parameter solution for these, we would get a much smaller error. And I think in that respect, the quasar solution is much more representative. And there we have already about 1 milliarc second for the quasars. And I don't see any reason why the stars should be worse in DR2, in the same magnitude range.
This might be a question for Paola regarding the cross-matching. To be clear, where were the proper motions for the external catalogs used exactly? Do you know?
We didn't use the proper motion from external catalogs. We just used the proper motion from TIGAS, only for the TIGAS subsample.
More questions?
I think it's in case time for coffee, is it?
Yeah. It's 4, so I think we have made, sorry, there was quick final question before coffee break. So thank you, we are in the right time.